Uranus, the shimmering blue ice giant, is one of the most peculiar planets in our solar system. Not only does it stand out as a planetary maverick, but it also remains one of the greatest research mysteries. Despite having been visited only once by Voyager 2 back in 1986, Uranus continues to intrigue scientists due to the sparse data collected during this fleeting encounter. Over the years, researchers have been able to uncover a number of remarkable and puzzling features about the planet. These characteristics have been as astonishing as they are baffling. For instance, Uranus orbits the Sun on its side, unlike any other planet in the solar system. Its magnetic field doesn't just have two poles, as we might expect, but four. Additionally, its surface temperature is an icy -216 degrees Celsius, far colder than it should be based on its distance from the Sun. These anomalies have left astronomers scratching their heads for decades, and only now are we beginning to unravel some of the mysteries surrounding this enigmatic world. The puzzling nature of Uranus has prompted an ongoing exploration of its composition and behavior. One of the most intriguing aspects of this icy giant is its magnetic field, which, as mentioned, has four poles rather than the expected two. This anomaly has baffled scientists, who are still trying to understand what could be responsible for the planet's complex magnetism. However, a breakthrough in understanding Uranus's magnetic field recently came when researchers re-examined old data collected by Voyager 2. While the probe's 1986 flyby provided valuable insights, it had also captured Uranus in an exceptional state due to a powerful solar storm that had recently occurred. This solar storm compressed Uranus's magnetic field and caused the surrounding plasma to be stripped away, which led to unusual conditions in the planet's magnetosphere at the time. The particles Voyager 2 detected were actually high-energy electrons, which were filled into Uranus's radiation belts by the solar storm, not by the usual sources of plasma. This unusual scenario meant that Voyager 2 had observed Uranus in a rare, non-typical state, which likely happens only about 4% of the time. Had the spacecraft arrived a few days earlier, it would have seen the planet in a more typical, less extreme magnetic condition, which could have helped explain some of its strange features. While this discovery has certainly advanced our understanding of Uranus, it's only one part of the mystery. Another intriguing aspect of the planet is its ever-growing family of moons. In a surprising development just a few months ago, scientists detected a previously unknown moon orbiting Uranus. This discovery brought the total number of Uranus's moons to 28. The new moon, tentatively named S223U1, is the smallest of Uranus's known satellites, measuring just 8 kilometers across. The discovery of this tiny moon only adds to the complexity of the planet's satellite system and provides further clues into the history and formation of the planet. Yet, despite the excitement surrounding the moon's discovery, many of the most fundamental questions about Uranus remain unanswered. For example, scientists are still left wondering about the true nature of Uranus's magnetic field, its strange tilt, and the mechanisms that govern its extreme cold. In terms of planetary magnetic fields, the case of Uranus is particularly puzzling because it doesn't follow the typical pattern seen in planets like Earth. Earth's magnetic field is generated by convection currents in its liquid outer core, which work in tandem with the planet's solid iron core to create a dipole magnetic field with two opposite poles. However, Uranus does not appear to have a similarly thick convective layer, which is why its magnetic field behaves so differently. The current models suggest that a non-dipole magnetic field can be generated if convection currents are confined to a thin, distant layer of the planet's interior. Scientists know that the interior of Uranus consists of a solid core surrounded by a mixture of water, ammonia, and methane, all of which could be conductive and therefore capable of generating a magnetic field. But the exact structure and behavior of Uranus's interior remain largely speculative, as the deeper layers of the planet have never been directly observed. One particularly wild theory posits that Uranus's interior might be a planetary diamond, formed under the immense pressure and temperature within the planet. According to this theory, hydrocarbons in Uranus's interior could be broken down and compressed into diamond crystals, creating a diamond rain deep inside the planet. This diamond rain could potentially explain the planet's unusual multipolar magnetic field, as the diamonds might interact with the surrounding gas and ice, setting convective currents into motion. These currents could, in turn, contribute to the planet's strange magnetism. While this theory is tantalizing, it remains speculative and is based on models of extreme conditions that have not yet been confirmed. More recently, a different approach to explaining Uranus's magnetic field has been proposed by Professor Burkhard Militzer of the University of California, Berkeley. Militzer's team used high-resolution computer simulations to model the behavior of methane, water ice, and ammonia under the extreme conditions believed to exist inside Uranus. The simulations revealed a surprising result: the water, carbon, and nitrogen inside the planet appeared to separate into distinct layers that could not mix with one another. At the top of the planet's interior is a conductive layer of water and ammonia, which is about 8,000 kilometers thick and may be partly liquid. This layer is thought to be where the convective currents responsible for Uranus's unusual magnetic field originate. Just beneath this layer lies a similarly thick zone of nitrogen-containing hydrocarbons, which become denser as pressure increases deeper inside the planet. According to Militzer's theory, the separation of these layers prevents the vertical flow of materials, which could explain why Uranus's magnetic field is so unlike that of Earth or Jupiter. While this new theory is a step forward, it is still in its early stages and will require further testing. Researchers hope to validate this theory through laboratory experiments under high pressure, or even through direct exploration of Uranus in the future. However, the prospect of a mission to Uranus remains distant. Currently, there is no active space program that is ready to undertake a dedicated mission to the ice giant. The most advanced concept for such a mission is the Aeneas project, proposed by the European Space Agency, ESA. This mission would involve two separate probes, one of which would be sent to Uranus and the other to Neptune. If this mission comes to fruition, it could take nearly a decade to reach the outer reaches of the solar system. Yet, despite the potential for such an ambitious mission, the timeline and feasibility of Aeneas remain uncertain. In the meantime, scientists continue to study Uranus using data from Voyager 2 and other space-based telescopes. These observations have revealed that Uranus's rotational axis is tilted almost 90 degrees, making it stand out from all the other planets in the solar system. Researchers believe that this extreme tilt may have been caused by a massive impact that occurred in the planet's early history. This collision may have been with a protoplanet that was twice the size of Earth, and it is thought to have sent ice and rock crashing into Uranus's core. This violent event could also explain some of the other strange features of Uranus, including its multipolar magnetic field and its inexplicably low temperatures. Indeed, one of the most striking characteristics of Uranus is its extreme cold. Despite not being the outermost planet in the solar system, Uranus is the coldest, with minimum temperatures reaching as low as -224 degrees Celsius. This coldness may be a result of the same collision that tilted the planet on its side, as the impact could have trapped vast amounts of ice in the outer layers of Uranus's mantle. This, in turn, would have disrupted the planet's heat flow, causing it to remain much colder than expected. While much of this remains speculative, the ongoing research into Uranus's mysterious properties continues to deepen our understanding of this distant and bizarre world. As we look ahead, there is still much to learn about Uranus. While some questions have been answered, many remain unresolved, and the search for a more complete understanding of this ice giant is ongoing. The planet's exotic magnetic field, strange tilt, and extreme coldness all point to a complex and dynamic interior, one that will require further exploration to fully comprehend. Whether through more detailed observations or future space missions, Uranus will undoubtedly continue to be a subject of fascination for astronomers and planetary scientists for years to come. The enigmatic ice giant may still hold many secrets, but with each new discovery, we are one step closer to unlocking its mysteries. As scientists continue to dig deeper into Uranus's complex features, it becomes increasingly clear that this planet's uniqueness cannot be overstated. For instance, the planet's strange four-pole magnetic field is a puzzle that has perplexed researchers for years. Unlike Earth's typical dipole field, which has two opposite poles, Uranus's magnetic field is more like a highly irregular octopus-like structure, with four distinct poles. While it's long been suspected that Uranus's magnetic field is the result of some form of convection occurring deep within its interior, the precise mechanisms that lead to such an extraordinary arrangement are still not fully understood. The fact that Uranus has such an unusual magnetic field is not just a scientific curiosity, it is a crucial piece of the puzzle in understanding how planetary magnetic fields are generated in the first place. The universe is vast, and so are the mysteries. Keep exploring with Space Lab.